Bismillahirrahmanirrahim. I welcome you to C339, Data Communications and Computer Networks. Today we'll discuss first DNS, domain name systems. Domain name systems is basically it's the internet's directory service, right? So domain name system is the internet's directory service. So let me try to explain it with the help of an analogy. For example, in our real life, we can identify people either by using their names or by their social security numbers, by their passport numbers, right? Or maybe using their CNIC, right? But ordinary people prefer the more the more mnemonics means using the birth certificate names rather than social security numbers and CNICs. So in real time scenario, I would prefer calling you by your name, right? So I'll be taking help of mnemonics to call a person, right? So just as humans can be identified in many ways, so too can internet host, right? So similarly, we can identify an internet host uh, with a mnemonic, right? For example, yahoo.com or say CNN.com. These are the host names, right? And these host name, CNN.com or Yahoo.com, are just like your name's mnemonics, right? And yes, we know that we can also identify an internet host with the help of an IP address, right? Why? Because this, mnemonic or this host name, CNN.com or Yahoo.com, it does not give me detailed information about the location of the internet host. For example, using CNN.com, I cannot reach the CNN server, right? For that, I need to have, this IP address here, right? Either 32-bit when I talk about IP version 4 or 128-bit when I talk about IP version 6. The second reason for using this IP address to identify the location of the internet host is, and not using these mnemonics, is because these mnemonics consist of variable length alphanumeric characters, right? For example, the length of Yahoo is different from the length here in this host name CNN, right? And it can contain alphanumeric characters as well, and that's why hosts are identified by so-called IP addresses, and the important thing is we can use these IP addresses to reach the location of the internet host, right? So in order to, and obviously, being humans, what we will prefer? We will prefer IP address, or we will use mnemonic or host name to address an internet machine or an internet server. Obviously, the humans prefer what? Host names or mnemonics. But in order to reconcile these preferences, we need to have a directory service, just as DNS. What it will do is it will translate host name to IP addresses. So what this directory service or this DNS does for us is that it translates this host name, cnn.com, to IP address, right? And um, um, and you can say this is the main task of the internet's domain name systems, DNS. That is to translate the host name to the IP address. Why? Because because we prefer to use mnemonics in addressing host names. So we can say that a domain name system is a distributed database. So what it is? It is a distributed database that has all these mappings, right? Which is implemented in in the form of different DNS servers or name servers, right? So we have implemented this directory containing this mapping of host names and IP addresses on a hierarchy of DNS servers, right? And different application layer protocols, allows hosts to query these, distributed uh, servers or hierarchy of servers or distributed database to get what? To get um, the IP address against the name, means to have this mapping from address or name translation, right? So variety of the application layer protocols makes use of, or they employ DNS. For example, if I talk about the application layer protocol, if I talk about HTTP, so HTTP makes use of what? It makes use of DNS. FTP, since we have covered these protocols, or talk about SMTP. So all these and many other application layer protocols makes use of DNS to get this mapping of address and name, or get this address name translation, right? Obviously here it's important to note that this DNS adds an additional delay, and it can be sometimes substantial, that the desired IP address is often cached in a nearby DNS server in order to avoid this delay. For example, if I want to know the IP address against a name, so I have to query our DNS server, and this DNS server is maybe not near me, right? So this is there is obviously a delay involved here, right? So in addition to this translation of names into IP addresses, it also provides us other very important services. For example, it provides us host aliasing, right? DNS, this domain name systems, a distributed database containing this mapping of IP addresses and host names, also provides us other important functionalities such as, number one, host aliasing. Okay, a host name, with a complicated, or a host with a complicated host name can have one or more, alias names. Usually, a host name is not that simple; it's complicated. For example, a host name may look like similar to this one: relay one dot west host dot enterprise .com, right? So, and usually such a name is called canonical host name. What we call it? We call it canonical host name, right? And obviously, this is more complicated as compared to a simple host name. So what I can have is, um, I can have one or more alias names for this canonical host name. For example, I can use this name to address, host name to address this host. For example, enterprise.com. Enterprise.com. Or I can use another alias, for example, www.enterprise.com, right? Since our host name is canonical, right? Uh, and in order to use a simple host name, we can have one or more aliases such as enterprise.com or www.enterprise.com, right? So it's very important functionality of DNS is it not only obtains the canonical host name for a supplied alias name, but it also obtain the IP address. So what happens basically is, so when we write enterprise.com, so DNS does what for us? It get us this canonical name as well as the IP address. Okay, and the second important service provided by DNS is mail server aliasing, right? Mail server aliasing. Okay, so email addresses should be mnemonics. We know that, right? Like hotmail.com, yahoo.com, right? But the host name of Hotmail server is more complicated, right? It is again maybe something similar to this. Say relay1 dot westledge host dot hotmail dot com, right? So again, we need to do what? So we need to have, or we can allow a company's mail server and the web server to have the identical host names, like gmail.com or like Hotmail, or hotmail.com or like enterprise.com, right? Can be used for what? Can be used for email as well as for the web server as well, right? So here we need to have a mechanism using which we can permit this. What? Using the same host name for both web and email server or mail server, having the identical host names. And this is done using what? Using MX record, and that we'll cover in a minute, right? So, mail server or DNS using MX record allows a company to have identical host names for mail server as well as for the web server. Okay, and the third important, service that is provided by DNS is load distribution. Load distribution. So see, a DNS also performs load distribution among the replicated service, such as web servers. You know what? The busy sites such as CNN.com are replicated over multiple servers. So there is no one server implementing CNN.com. There is an array of servers. There's a form of servers implementing a busy site, right? So when a replicated server is addressed, or when I try to access CNN.com, a set of IP addresses is returned that are associated with one canonical host name. I repeat. So since I maintain CNN.com or more than one servers, so a set of IP addresses is thus associated with one canonical name. So when I address CNN.com, what this hierarchical DNS database does is that it returns me a pool of IP addresses mapped to a canonical name. But when it returns me or it gives me a list of IP addresses, it shuffles it rotates it so that the load can be distributed on these evenly distributed on these servers, right? So it does not only give me the list of the IP addresses mapped against the canonical name of, say, for CNN.com, but it also rotates it as well, right? So a DNS query or a reply message is sent within UDP datagram. So remember, up till now, whatever the applications at the application layer we have discussed by using TCP, right? So this DNS domain name systems makes use of UDP at the transport layer for the DNS query and reply messages. And these DNS queries and reply messages are sent over on port 53. Okay. So if we look at if we look at the implementation of a simple DNS design, it could have been one DNS server. Now the question is how I will implement this, the mapping of IP addresses and host names. So one simple implementation could have been that I have one DNS server, right? And every machine, can access or can connect to this simple or single DNS server. But what do you think? What are the problems with a centralized design here? If I have one DNS server, so the problem can be a single point of failure. So if I implement DNS on one server, the one problem can be it's a single point of failure, right? So we are just talking about the design possibilities. So one design possibility is that I'm implementing it on one server, and the drawback of such an implementation is single point of failure. Single point of failure. Okay, what else? Then maybe the traffic volume is huge on this one server. There are millions and billions of requests or query DNS query messages. So we may end up having a huge traffic volume. Okay, what else? Maintenance would be an issue, right? So if we have one single server, then the problem is that how we gonna maintain it, right? Then maybe it's not it's not a distant centralized database. I mean, maybe it's not close to all the queuing or all the hosts sending query messages. So distance is another issue, right? So this means one single DNS server is not a good solution, right? So that's why we need to implement domain name systems as as a distributed and hierarchical database, right? Where there are three classes of DNS servers, right? So we have this root DNS servers, right? Then we have top level domain TLD, top level domain DNS servers, and where we have this authoritative uh, DNS servers, right? So we have root DNS servers, we have top level domain, DNS servers, and we have authoritative authoritative DNS servers, right? And then we also have, local DNS servers, right? So DNS is implemented as a distributed and hierarchical database. Let's talk about these servers in a detail. So first we have, the root DNS servers. There are 13 root DNS servers, right? Around the world, distributed, around the world, and each, of these 13 root DNS servers is actually a network of replicated servers, right? So you can see here each site have, uh, other, or you can say a network of DNS servers. So there are in total, there are 247 root uh, servers. Okay, and that I'm talking as of fall, as of fall 2011, right? So there are total, 240. Obviously, there are 13 root name DNS servers, each having a network, and there are total 247 root servers as of fall 11, right? And then, what happens is that we first contact the root DNS server. The root DNS server is first, is contacted to get an IP address of a specific, uh, server, and then this root DNS server forwards it to top level domain server. Then the top level domain server forwards it to authoritative DNS server. That we'll see in a minute with the help of an analogy. Let's try to understand first that what is the main functionality of each of these servers in this hierarchy. Then we have top level domain server, right? So top level domain server is responsible for top level domains such as .com, .org, .net, .edu, etc., etc., and importantly, all of the country top level domains such as UK, uh, FR, PK, CA, right? And then we have. Uh, then there is a company known as, with the name, VeriSign Global Registry Service, that maintains the top level domain servers, means uh, .com, .org, .net, etc., etc., all these different domains. And then we have the authoritative DNS server, right? So this is an organization, the authoritative DNS server. It houses the DNS records, right? So it's organization's own DNS server, and it provides what? It provides the host name to IP mapping of organizations' addressable hosts that are addressable to the other host on the internet, right? And then we also have, it's not listed here, but we also have the local DNS server. Within the organization, we have division into different departments, and there are different hosts that are accessible. So we can have the local DNS servers as well, and this hierarchy, so that we can access that specific machine. So let's try to understand it with the help of a scenario, that how our DNS query, either it's recursive or iterative, is generated, and a response is received by the other machine. So let's assume that I have a requesting host here. Okay, so here we have a requesting host. Okay, and the requesting host is CIS dot polytech dot edu. Right, and then whenever a requesting host requests something, right? Say it requests GAIS or GIA.cs University of Massachusetts.edu. This is the host that this requesting host wants to access. The first point of contact here is the local DNS server. Local DNS server, and it has address dns.holy.edu, right? So the request will be forwarded to, and this is the sequence. So the request will be forwarded to local DNS server, say dns.poly.edu, and the host that wants to access, another host is cis.poly. This poly is for polytech.edu, right? Now, if we have this entry at the DNS server, it would be returned to the requesting host. But we, assume that this is not there in the local DNS server. So the request, would be forwarded to um, root DNS server. Remember, we have 13 root DNS servers and in total 247 DNS servers. So the request will be forwarded to root DNS server. So this is query number 2. So root DNS server does what? It looks at the database and returns the address of the top level domain server. So here we have in hierarchy, if you remember, here we have um, a top level domain DNS servers that are responsible for what? That are responsible for specific domains .com, .edu, .pk, .fr, and etc. etc. So now, after getting the address of specific top level domain server, the local DNS server forwards request to the specific top level DNS server, and this is request query number 4. And in response, the top level DNS server returns what? The address, the authoritative DNS server address, right? So remember, in hierarchy, we have root DNS servers, then we have top level DNS servers, and then we have what? Then we have here, then here we have authoritative. So here we have authoritative DNS server. Okay, and that is what? DNS dot umass dot edu, right? And now, after getting the address of this authoritative DNS server, the local DNS server of the host will contact the authoritative DNS server. This is query number 6, right? And now this authoritative DNS server has the mapping of the local addressable host, and the host that I'm interested in getting in contact is, say, GAIA dot UMass, University of Massachusetts dot, it's in CS. dot cs dot umass dot edu, right? And it it gives it sends back the IP address of the specific host to the local DNS server, and then this local DNS server sends it back to or provides it to the requesting host, right? So you can see there are total 8 queries here, and even if I have local, if I involve here, if you're getting it, if I involve here local DNS servers as well, then I have another couple of queries to resolve the specific host, accessible host. So these queries are either recursive in nature. These DNS queries are, they're either recursive or these queries are iterative. Right? For example, this query here is recursive, where I'm trying to ask the local DNS server for the address of the destination host, and all the other queries here are iterative. Why? Because every response is being returned to the local DNS server. So if I'm sending something to the root DNS server, the response is being sent back to the local DNS server. If I ask something, query top level DNS server, the request is being sent back to the local DNS server. If I'm sending something to authoritative DNS server, the request is being sent back to the local. So these queries. These queries are iterative in nature, and here this is recursive. So we can have another scenario to understand how the queries will will be processed if uh, these are totally recursive in nature. So let me we can remodel this scenario. So for example, I have this requesting host. Say cis.politech.edu, and I want to access the other host in UMass. So what I have to do is I will send or forward this request to the local DNS server. Okay, so this is request number 1, and now this request will be forwarded to the root DNS server, right? So this is query number 2, and now it will be forwarded to the top level domain DNS server, and now this is query number 3, and it will forward it to authoritative. So this is authoritative DNS server, that is dns.umass.edu, right? And this is query number 4. It will provide the address of specific host, right, to the top level DNS server. Then it will forward it to the specific root, and root will forward it to the local DNS, and then it will forward it to, right. So now this sort of the queries this is a scenario that involves all recursive DNS queries. Okay. Right. So, but usually, this is how our requests are. Or DNS requests are generated, and response is generated in a typical internet scenario. All right. So, and obviously, requesting the distributed servers involves a delay, maybe. So we need to have local DNS caching in order to mitigate the delay. And quickly, I would like to comment on the way DNS distributed database store resource records. So usually the resource record that is stored by, so I'm talking about resource records. So it has 4 tuples. It has a name, then it has value, and it has a type, and TTL. TTL stands for time to live. This is time to live. I mean, time to live means for how long we're gonna maintain this entry in our cache. So if this type is A, if in type we have, if type is equal to A, then the name is the host name. Then name is a host name, and value is IP address. Right? Value is the IP address. Okay. But if the type is NS, then the name is the domain, and the value is the host name of an authoritative DNS server, right? So let me write it here. The name is a domain, and the value is the host name of an authoritative DNS server. The host name of an authoritative DNS server. For example, the name is foo.com, right? And the authoritative DNS server is dns.foo.com, right? And type we know is NS. Okay, and then we have obviously TTL, the value for which we will remember this entry. And if the type is, for example, CNAME, then we have the canonical name here, right? That is, the name is the domain name, like foo.com, but the value is what? Value is the canonical name. That is, say, relay1.par.foo.com. And obviously, the type here is CNAME. Means we are interested in getting what? The canonical name, right? And then remember I discussed with you the MX record, and the type is what? The type is equal to MX that we were discussing in the services provided by the DNS for mail aliasing here. The name is Again, the domain name, which is who.com. But the value is what? Value is the canonical name for the email server. And this is what? This is the MX record. Remember, we talked about it that MX record helps us, a company, to do what? To have the same, same domain for, or same host name for the web server as well as for the email server. Okay. So, so this, pretty much concludes our discussion about the DNS or domain name systems. So let's talk about peer-to-peer network. So in peer-to-peer network, so there is no one specific machine providing services. All the machines or the hosts are participating. The hosts are providing at the same level. They're providing services to each other, right? It's self-scalable, that we'll see in a minute, right? And the popular examples of peer-to-peer applications are file distribution, such as BitTorrent application and streaming, Concon, and then voice over IP. Like Skype is also what? Skype is also a peer-to-peer application, right? So before we talk about a specific peer-to-peer application that is BitTorrent, let's quickly talk about and let's try to compare the peer-to-peer application and client-server applications, right? So, the question that we want to answer in order to understand these two or compare these two types of application is how much time it requires to distribute a file having a size F, right, from one server to n peers, both in client server architecture and then peer-to-peer type of applications. So, in order to understand, let's understand the knowledges that are the notations that we are using here. So here, this US U sub is server's sending rate, right? Is the rate at which the server is sending data to a host. Okay, and this server has a file having size F. Clear? And now, similarly, this D sub I is the download capacity of a host, and similarly, U sub I is the upload capacity or the sending capacity of a host. Okay, so these are the notations that we'll be using. So it's important for us to understand these notations. So first is the U sub S. This is the rate at which a server is sending a file to host. F is the size of the file that we want to download. And similarly, if we talk about a host, D sub I is the download rate of a host, and U sub I is the upload rate of a host, the rate at which a host can upload the. And let's assume that there is no bandwidth constraint here. The network bandwidth is in abundance, right? So there is no issue of the network bandwidth, and then still we'll see how we can have a problem in client server environment here, right? So if I talk about, if these notations are clear, if I talk about distributing a file in a client server environment, then the server transmission must sequentially send or upload n copies. For example, if there is one host trying to access the copy of the file, the server will send this copy to one host, then it will send this copy to the second, and then the third, and the n number of hosts. So the question is how much time it takes to send one copy of the host to one host, since it's sending sequentially. So the number one question is, what is the time required to send one copy of the file? That is very simple. We will divide the size of the file by the sending rate of the server. Remember, F is the size of the file, right? And this is what? This is the upload capacity or the sending rate of the server, right? So if I want to send one copy of the file to a host, how much time it will take? I will divide the size of the file by the sending rate of the server. But now, if there are n number of hosts and want to have the copy of the same file, how much time it will take to send n copies? That is n number of copies divided by the sending rate of the server, which is the same, u sub s, right? So similarly, if we talk about the time required by a client to download a copy of the file, so that is what we know, this that the min is the minimum client download rate, right? The download rate of a client, and how much time it will take by a client to download a file, the size of the file divided by the download rate of the client. So if I talk about the time to distribute a file to n clients using client server architecture, so this is what? This is the distribution of a file in a client server environment. So it's greater than equal to maximum of these two. What is this? Time required to distribute n copies of a file. Yes, no? Yes. And what is this? File size divided by the download rate of a client. Time required to download a file by a client. Download the file by a. So the distribution time required in a client server environment is basically maximum equals to or greater than maximum of these two. What it is? The time required to distribute n copies of a file, or the time required to download a file by a client, whichever is higher. So what do you think? If this n is increasing, I mean, if I have to send n number of copies, which time will be more? Obviously, the time to distribute n copies of a file. So what I'm saying here is that if n increases linearly, there is a linear increase in n. What is happening here? I mean, we are maybe increasing here. So we are increasing here what? The number of hosts. So what this is doing? This is increasing n linearly, right? But what about this? The sending rate of the server is the same, right? So this means what? This will take more time to transfer a copy of the file if if I keep on increasing the number of clients requesting the same, file. N is increasing, the N is increasing here. So in this scenario, the N is increasing, but there is no increase in the upload capacity of the server. So this means it's not scalable. Means if I add more number of clients and they are requesting the copy of the same file, this will increase the file distribution time in a client server environment or scenario. So that's why. So if I want to scale it up, what I have to do then? What do you think? What we have to do? I have to add more servers here. More servers here, right? Only then, the time can be to transmit a file can be reduced. Otherwise, not self-scalable. It's not scalable, right? Okay. But now let's compare the file distribution time in a peer-to-peer environment. And again, here we We are familiar with this. The time to send one copy is what? The time to send one copy is the size of the file divided by the sending rate of a server or a machine, or a server, say in this case. A server is there, let's assume, right? And we are also familiar with this time. That is what the minimum time required to download a copy of the same file by a client. But if all these clients are taking part and sharing the copy of the same file, then what is happening? Now, I'm assuming a scenario where every client is having a copy of the same file or a chunk of the same file. And now all these clients are not only sending or downloading the copies, but also sending the chunks of sharing the chunks of the same file with the other clients as well. So what will be the distribution time in a peer-to-peer network? It would be maximum of equal to or greater than the maximum of these three. I mean, what is this? This is the time to send a copy of the file by the server. This is the time to send what? Or time to download a copy of the file by a client. What is this? This is the time to download n copies of the file. And now see what is happening here. The max upload rate is what? Is the upload rate or the sending rate of a machine plus the total number of machines that are participating in this process. So if this n is increasing, I mean, if there are more number of hosts requesting for the same file, right? But this UI is also increasing. Why? Because all these hosts are now also participating in this sending receiving process. These are all not only downloading the files, but these hosts are also uploading the files to the other machines or the other clients. So if there is a linear increase in n, there is also linear increase in the sending capacity service or sending capacity of the network also. So this is how this, if I add more number of devices, this will self-scale the system in a peer-to-peer arrangement. Why? Because all the peers are participating in this sending receiving process here. Clear? And let's try to understand this with the help of this, with this example, this chart, right? So on x-axis we have the number of nodes, right? 5, 10, 15, so on and so forth. And here we have the minimum distribution time. And here we have a line representing the time required to distribute a file in a client-server environment, and the time required to distribute a file in the peer-to-peer arrangement. So look at the graph of client-server environment. As the number of nodes are increasing, the time to distribute a file is also increasing linearly. Why? Remember, it was sending n number of copies of a file divided by the upload capacity of the server. So if the number of nodes are increasing, the n is increasing. So the time to distribute the file is also increasing. So if n is increasing, it was 5, 10, 15, 20. So there is a linear increase in the time required for the distribution of the file. But on the other hand, look at the graph of, in peer-to-peer arrangement. If the number of files or the number of nodes are increasing, the time to distribute the file is decreasing. Why? Because now this n is not only increasing, but also we have what? We have all the nodes contributing in this sending receiving process. If this n is increasing, the number of nodes sending or sharing the copy of the file is also increasing. So clearly, the time required to distribute a file in a peer-to-peer arrangement is less, or it decreases as the number of nodes are increasing. But on the other side, in a client-server environment, if the number of files or the number of nodes are increasing, there is an increase in the file distribution time. So the peer-to-peer, networks are, or the applications are self-scalable. Right. So let's quickly talk about peer-to-peer applications such as BitTorrent, see how it works. So BitTorrent is a file distribution application, right? So in a BitTorrent like application, we have a torrent that is basically the collection of all the peers participating in the file distribution. So torrent is what is a group of peers participating in the file distribution, and then we have we have a tracker. Tracker is basically a server that is tracking, or you can say it's an infrastructure node uh, for each that is tracking each torrent, right? So every time peer participate in the distribution of a file, it registers itself with the tracker or this infrastructure node, right? And then we have a chunk. Chunk is basically the size of a chunk of a file is 256 kilobyte, right? This is 256 kilobytes. I should have, okay, and let's see how it operates. So let's assume that Alice arrives in the system and she wants to access a certain file. So what she does is that it obtains a list of the peers participating in the file sharing, in a specific file sharing process that we call a torrent, right? So what happens is that this tracker provides Alice a list of the peers participating in the exchange of a particular file. So initially, 50 nodes are, or 50 peers details are forwarded to the Alice, right? And Alice start exchanging the files with these peers, right? And what Alice does is it keeps calculating its transfer rate with all of its peer every 10 seconds. So Alice, after every 10 seconds, recalculates or calculates its sending rate or receiving rate with all the peers, right? And Alice, identify the 4 top peers that she has the highest ascending rate. And after every 30 seconds, Alice, picks another additional neighbor and again calculates its ascending rate with that peer. So peer joining the torrent, if for example, as we have the case in this example, Alice just arrived and she has nothing to share, but she can get a list of the torrents, and over the time she can participate in this file sharing process, right? So while downloading a peer also uploads chunks to the other peer, right? So it's a trading algorithm. So uh, peer may change peers with whom it exchange. How? We'll see in a minute in the next slide. So a peer can come and go, right? Or you can just download a file, or you can disconnect from the internet, or you can exit the application, close the application selfishly, or you can selflessly keep on participating in this process. So at any given time, there are different peers that have different subsets of files. Alice, first of all, request for the rarest file chunk first. So this is important. So, for example, there are 50 peers participating in the file sharing process. Every peer has a certain chunk of the file, but Alice would request first the rarest chunks from the participating, or from the peers that she's interacting with, right? So Alice selects what the four peers here. Alice selects the four peer. How? Because these are the peers that have the highest, sending rate. Their sending rate is highest. Okay, and it recalculates the top four every 10 after every 10 seconds. Alice recalculates its top four providers, and after every 30 seconds, Alice optimistically unchoke. Optimistically unchoke means hoping that the other peer will also share the chance with the Alice. So what I'm saying is that after every 30 seconds, Alice will unchoke, say, another peer, optimistically unchoke another peer, say, Bob, hoping that Bob will be one of its four top providers, right? And Alice start sending data, and Bob, say, reciprocates and also sends data at a highest rate and becomes one of the top four providers of Alice. Right? And in a similar way, Alice, after every 30 seconds, or Bob, after every 30 seconds, keep on optimistically unchoking another, peer to find if it is one of the four best provider of Alice or Bob. So in this way, in this application, a peer keeps on changing its top four providers and keep on getting the chunks of the files. Right. So before we conclude chapter number 2, our discussion on the application, I would like to discuss quickly with you distributed hash tables. This is the implementation or a simple database implementation of peer-to-peer networks. So quickly we'll have a few words about um, distributed hash tables, and then we'll try to conclude today's lecture. So switch to the okay. So I just want to say a few words discuss quickly um, distributed hash tables. That is DHTs. Okay, so distributed hash table is used for the implementation of peer-to-peer networks, or it's a database of peer-to-peer network. So we can have a simple implementation database implementation in a peer-to-peer network where we can say where we can have a record in the form of a key value pair. So we have a pair where we have key and so a simple database implementation in a peer-to-peer network would be a key value pair, right? Where we have a key and the associated value. So what we do basically, we query the database with a key, and what we'll get in return? The value, right? So for example, key is your CNIC and the value is your name. So one possible implementation of building such a network can be straightforward, right? That we have a centralized database that have all the keys, these pairs stored there, and whenever a machine needs to get the value of a key, we'll send this query. But obviously, um, uh, you know, um, obviously this would be a single point of failure. There will be more burden on a single server containing all these records. So what we want to do is we want to have a distributed, we want to build a distributed peer-to-peer version of such a database, right? So simple implementation is possible that where we are storing all these pairs on a single server. But what we want to build, we want to build a distributed peer-to-peer version, right? And Such a distributed peer-to-peer version is called what? Or is referred to as such a distributed database is referred to as a distributed hash table. Distributed hash table or DHT. Okay, and so what we want to do is basically that we want to randomly scatter the key value pair across all the peers, right? So what's the purpose or the motive is, or that we want to randomly scatter the record, that is what? Key value pairs across all the peers. Okay, so instead of storing on a single server, since it's a peer-to-peer network, so we want to build it distributedly, and how that is to scatter randomly the key value pairs across all the peers, and then we can have a list of IP addresses of all the participating peers, and have a list of the IP addresses of all participating peers. Okay, but such an approach is completely unscalable. Why? Because that each peer has to maintain a list of the IP addresses of all the participating peers, right? And which is not scalable, right? So we want to make this distributed hash table, or we want to make it scalable, such a system scalable, right? So what we can do is we can say, okay, fine, there's another way to do it, that each um, identifier is is an integer in the range of, so what I can say is that instead of using IP addresses and maintaining all the IP addresses of all the machines or peers, I will use identifier, and each identifier um, is an integer, and it's in the range of 0 to 2 raised to power n minus 1. Okay, say for some record n. So rather than storing all the IP addresses of all the participating peers, we will maintain an integer identifier which is in the range of 0 to 2 raised to power n minus 1 for some fixed, say, n, for some fixed n, to just make it easy for you to understand, for some fixed n. Okay, and now assign each key value pair to the peer whose identifier is the closest to the key. For example, the closest successor of the key. So what I'm saying is, now if I want to sign a record to appear, so what I'll do, I will assign each key value pair to the peer or the machine whose identifier is the closest to the key. Okay, so instead of storing the IP addresses and all that, so we have what we have the identifiers, which are integers. Then the next question is that how we gonna store the pairs on each identifier or the peer that is being identified with the help of an integer value or the identifier. So we will assign each key value pair to peer whose identifier is closest to the key. And what is the definition of the closest here? There can be a variety of the definitions of the closest, but here the closest means the successor of the key, right? The next value of the key. But such an approach requires each peer to keep track of all the peers in the distributed hash table, which is again impractical for a very large scale system with millions of peers. So this was probably an alternative, but again here the problem is that we have to keep each peer. The problem with this approach is also that each peer to record or to keep record of all other peers. Okay, right? So again, it's not scalable. But by the way, before we move, and discuss another alternative and try to conclude the topic, this key value pair, since it has two entries, key and the value. So what we do basically is that we apply a hash function here that converts this key value pair into an integer, right? Value. And that's why we call it what? We call it hash tables, distributed hash tables. So has the one-way function where when we provide this key and value, it gives us an integer value. So since we are also representing each node with an identifier, integer identifier, so this record also needs to be represented in terms of integers, but this record has two tuples, key and value, in order to be represented in the form of an integer. So what we do a hash of the pair. We perform a hash function that converts this key value into an integer. Okay, and that's why its name is distributed hash tables. Okay, so the solution to again such a problem is circular distributed hash table. So hash is what the integer representation of the pair. Table is containing these the records, and distributed means we have distributed it across the different pairs. And now we are trying to evaluate. We're trying to refine this process from a single machine to distributed across the different peers, and then from identifying these peers from IP addresses to the integer values, and then now we have come to the circular distributed hash table. And the point here is that each peer has to, instead of each peer keeping record of all the other peers, each peer will keep record of its predecessor and successor node. So peer 1 will keep record of, say, peer 3, and peer 3 will keep record of peer 4 and peer 1, and peer 5 will keep record of peer 4 and peer, say, 8, and peer 8 will keep record of peer 5 and peer 10, and peer 10 will keep record of peer 8 and peer 12, and peer 12 will keep record of peer 12 and peer, right? So this is what this is called a circular, distributed hash table, where each peer keeps track of its immediate successor and immediate predecessor. That is modulo of 2n, right? Modulo. Okay, right. And what happens in the circular arrangement? For example, if I want to access a key 11 and node is 3 here, what will happen? Node 3 will forward it to, is this key 11, where this key 11 record will be stored, by the way. The successor of, say, 10, 11, somewhere, it's on node 11, right? So what will happen here? So node 3 will forward it to node 4. 4 will forward it to node 5. 5 will forward it to 8. 8 will forward it to 10, and then to the respective node having this key. Okay? But obviously, you can see here, still the number of yes, the advantage of circular DHT is that instead of having the record of all the peers, a peer only maintaining the record of its predecessor and successor. But in a worst case scenario, we have to maybe end up having n passes through the peer, through the peers here, and through the circular distributed hash table. Okay. Again, it's not efficient. So what to do then? So we'll say, okay, fine. A peer also keeps record of some more peers other than the predecessor and successor. For example, peer 3, just for the sake of example, peer 3 keeps record of peer 8. Peer 4 keeps record of peer 10. Peer 5 keeps record of peer 12 in addition to its predecessor and successor. And peer 8 keeps record of peer 15, right? And peer 10 keeps record of 1. Peer 12 keeps record of 3, and peer 15 keeps record of. Now this network here, this network here is called an overlay network. As not, these links are not physically there. This is overlay network. These are not the actual physical links, right? Connecting these peers together. But we using this overlay network, now we can reduce the number of passes required to reach a specific peer. For example, now if at node 3 I want to reach key 11, so key 11 is closest to 8. So instead of forwarding it to node 4, 3 will forward it to 8, and now 8 will forward it to 10, and then the peer containing the required key. So the next question is, what do you think? How many number of other peers a node or a peer need to keep track of in addition to its predecessor and successor nodes? Well, so there are many different implementations provided by the research community, but they say the running time should not be greater than within this range, big of log n, right? So whatever you decide, how many number of the extra peers that a peer needs to keep track of, other than the predecessor and the successor node, it should not. It should be well within this range, right? So distributed hash table is basically the implementation of the peer-to-peer database. Hash is converting the key value pair into the integer. That's why we do this hash function. We maintain these tables, records, and in a distributed fashion. That's why we call it what? Distributed hash across all the peers. That's why we call it distributed hash tables, and there are different implementations. And the implementation that we have we are concluding our discussion with is known as circular distributed hash table. So this summarizes our today's lecture, and this also summarizes our discussion about the application layer, where we have discussed different applications, the nature of applications, where we have covered the working details of and the technical details of different application layer protocols and applications that we make use of in our daily life